Hello, this is the third part of the 2013 PAT, so we're still on the physics questions, but these are the slightly longer ones between the multiple choice ones and the long one at the end. We've got a four-wheeled car, mass 1,000 kilograms, resting on the ground. Each tyre is inflated to 2 bar. Oh, well, that's what 1 bar is. What area of each tyre is in contact with the ground? Assume a uniform distribution of mass. Right, so we can pick any one tyre. We want the area. So pressure is force over area. So area is force over pressure, which is going to be, well, the force is going to be a quarter of the weight. So that's 250 G. So in this paper, that's 2,500. The pressure for one tyre is 2 bar. So that is 200 and then another 3 zeros. Cancel a couple of zeros top and bottom. So we've got 25 over 2,000. So that's going to be 20 times 4, 1 over 80. 1 over 80 is 100 over 80 times 10 to the minus 2, which is equal to 1 1/4. 1.25 times 10 to the minus 2 meters squared. Right, so that's a nice start. Right, now we've got a bit of mechanics. We've got two masses. I mean, is there anything in the text that isn't in the picture is the thing. So M and M, they're both there. Massless string, fixed length, on a slope, angle alpha, that's in it. Pulley P, massless, yep. Ignoring friction, calculate the acceleration of mass M, tension in the string. So we'll say we've got acceleration there, and we've got tension, we've got weight of mg, we've got a weight of capital Mg, we've got tension here, and we'll say we've got acceleration there. So we can do a couple of F equals MAs. So we're going to have that T minus mg sine alpha is MA, and then for the big M we'll have mg minus T equals MA. So that's all good. So we want to get T and A, so well, we add them together first of all, which will give us the mg minus little mg sine alpha divided by the sum of the masses. That's going to be our acceleration. That's always the easier one to get with the accelerations. I've just noticed here as well that they're asking us for what is the condition for the masses to be stationary. So if they're stationary, if they told us that they're starting from rest, what have we got? Two connected by a massless string. So it doesn't say they're starting from rest. So, condition for masses to be stationary, you're thinking, well, okay, so assuming, we'll have to assuming starting from rest, because they haven't said. I mean, if you've got zero acceleration, but they're already moving, then saying A equals 0 isn't really going to help because they'll just keep on going. But if they are starting from rest, then we can say stationary. We've got to come back for T, obviously, when A equals 0, i.e. we've got that, well, the numerator here has got to be equal to 0. So we'll have M, capital big M, is equal to little m sine alpha, because the G's will cancel. So we've already done that last bit as well. Now we just have to get T. So let's scroll down a bit because this is going to take a bit more messing around. So we've got that T is equal to capital Mg minus capital MA. So, all right, let's factorize that then. So we take the M outside. We've got a G. What was our A? That's all our A. Okay, let's multiply that by M plus M and take an M plus M outside. So I'm putting this A in here that we've worked out previously. So where was I? So I'm going to have to take off now the numerator. So minus capital Mg, and then that'll become a plus Mg sine alpha. So, oh, that's a big bracket. Just zoom that up a bit. So what am I going to have here? This, when we expand out the bracket here, we have an Mg that will cancel with that Mg. So that's going to be, let's put the M over M plus M bit back in. Then we're going to have little mg, and that's going to be, and then we've got plus mg sine alpha. Okay, So we've got big M, little m, g, divided by m plus m, multiplied by 1 plus sine alpha. Cool. So is that everything they wanted? So we've got t, we've got a, and we've got the what was it? The condition for the system to be stationary. So yes, we've done all the bits there. Quite a lot of parts in that, but that's more or less a standard A-level mechanics question. So it's not really offering anything new. So we're on solid ground when we see these sort of questions. Right, so push on to the next bit. Right, this one, I think I did this earlier in while we were going through classical mechanics because it's a very interesting question. Projectile of this mass, 0.2 kilograms, moving at 122 meters per second, hits this 12 kilogram ball hanging on a string. Right, we need to see how far it goes up in the air. You know, they're going to combine. This is going to swing up in the air. The way this can go wrong is, which we don't know if this is an elastic or inelastic collision. Well, we do in the fact that they combine, so it's going to be inelastic. So you can't start with conservation of energy. This is the point with collisions. You always have to start with conservation of momentum, because we know that momentum is always conserved through a collision, but we can't say that about energy. So we have to start off with this and say that 0.2 times 122 is the combined mass times the new velocity. So that means we can work out the new velocity. And I've done this quite nicely, that dividing that by that gives us 10. So we've got the new velocity is 2 meters per second, makes things nice and easy for us. Then we can do the conservation of energy swinging up in the air, as in our half mv squared is equal to mgh. So cancel the m's. The h that we want to calculate is v squared over 2g, which equals 2 times 2 over 2 times 10. So 2 over 10, 0.2 meters. If you don't do the conservation of momentum, you try and do this with conservation of energy, and you get a much higher velocity here, and the ball will go much higher. But this is the thing, when things merge with each other, you get two things hit and combine, where you haven't got an elastic collision. That is an inelastic collision. There's nothing you can do about it. There's not some setup where you can say these two objects have combined after collision and oh, it's still elastic. Well, no, it isn't. So always do conservation of momentum first when you are looking at collisions. It's the only thing you can be guaranteed of. Right, question 19. Monochromatic point light source of wavelength lambda shining through two narrow slits separated by distance d. D is of the order of the wavelength on a screen which is distance d away, where d, big D, the distance of the screen, is a lot greater than the distance between the slits. So this is the classic double slit experiment. Right, so sketch the pattern of light intensity observed on the screen. So I suppose it opens debate as to what they mean by sketch the pattern. I'm going to go for a graph of having intensity by distance on the screen. So this is called our X, where this is distance on screen. So not to the screen, but on the screen. What sort of pattern are we going to see? So sketch the pattern, explain why they're minima and maxima, and then, oh, we need to compare for red or green. Right, okay, so let's change colour and draw something for red, so I've got something to compare it to. So we get these peaks and troughs, don't we? So we get high intensity in the middle, then it's going to drop down, then it's going to come up, and so on. You don't get that much difference in the, you don't get much drop off in intensity from fringe to fringe, because the screen is a long way away compared to the separation of the slits, and it's the separation of the slits that's determining the difference in path length. Yeah, well, essentially the wavelength is determining this. I mean, they're the same thing. They're of the same sort of order. So you're not getting that much difference in path length. So you're not getting much drop off in intensity because you've traveled so much further. it's the difference between traveling that far or traveling, that far. You've added on like a dot at the end. I mean, if you wouldn't even be able to see it drawing it on here. So the intensity is not changing much. It's more or less constant. So why have we got these maxima and minima? Okay, so we're getting maxima when the light from the two sources is in phase. Two slits in phase. So you could then say this is constructive interference. So you want to get all of these things in, all the usual words. So we've said here that we've got in phase and constructive for the maxima. Then you can say for minima, you can write the same sort of thing, but you can say out of phase. And then you could even say, pi out of phase maybe. Destructive interference. Then you can say that we've got multiple fringes because there are multiple fringes. So because what are we trying to say? Explain why there are minima and maxima. So it's asking for why we've got multiple ones, multiple fringes, because there are multiple different path lengths from the slits. Path lengths from slits that produce 0 and pi phase differences. So that's why we're getting these multiple fringes on here. We're not just getting one of them in there because we've got multiple different path lengths. So I mean that's fine. I don't know what else I'd really want to say about that. If lambda corresponds to red light, which is what I've drawn here, what would the pattern look like for green light? So if we were going to change over to green and then say the same sort of thing, well, green diffracts less than red because it's a shorter wavelength. So the fringes will be closer together. So we're going to end up having it look more like this. We just need it squished up a bit. Okay, I'm exaggerating it maybe compared to my really wonky lines as well. But you want to just have it that the fringes are closer together. So that's what's going on there. Make a sketch on the same scale. So you could either draw them side by, well, actually you wouldn't have red and green pens in the exam. So draw two graphs, one above the other, showing how they're different. And then put in something that, green has got, if the wavelength has gone down, the separation x goes down, the x separation goes down as well. So yeah, that's a standard double slit question. So have we got any more? No, we're on to the long question next time. So that's completed those, whatever it was. Again, a nice set of questions covering a nice range of areas. I'm liking this paper so far. 2013 it's a nice paper, plenty to think about, challenging, not crazily difficult, but not crazily easy either. So